Hello, students. Welcome to today's session on Newton's laws of motion from the unit Laws of Motion. We are considering all the three laws of motion given by the famous physicist Isaac Newton. So Newton's first law, it deals with the state of rest. It deals with the state of a body, basically, to be more precise. So what does it say? It says inertia. It describes inertia. Inertia is the virtue of a body. Like by virtue, what a body holds. Like we say that this person holds a lot of inertia, so he might be finding it difficult. He might be exhausting in a day, in a routine life cycle. Yes. So inertia is that particular effect of physics. Yes. So a body continues in its state of rest or uniform motion unless acted by an external force. A body continues in its state of rest or uniform motion unless it is acted by a an external agency, which you can call as a force. Yeah. This is the first statement or the first law given by Newton. First law, you can call it NLM first. Like if we place a card over a cup, If this is a cup, let's suppose this is a cup. Yes, this is a cup, and I'm placing a card over it. And within a fraction of second, I'm just displacing the cup. If I'm doing that, the card will not leave its position, and the card will fall down. This particular effect of physics is known as inertia, and henceforth justifying the statement of Newton, which Newton concluded in terms of the first law. Because a body is continuing, the card is continuing to be in rest, and because we are not applying the external force on the card, we are applying the force on the cup. We are applying the force of pull. We are pulling the cup, so the card is landing down. Easy as that. This is the first law of Newton. What we can for example, we can write a card stays in the state of rest when we pull the cup over which it was placed beneath. Yeah. Likewise, after the first law, we will be considering Newton's second law. You must have heard, like, why does it hurt more if someone throws a heavy stone at you than a tennis ball at the same speed? This is a person and you're throwing a tennis ball and someone is throwing a stone. Speed is all same. It's 30 meters per second. But the stone hurts than a tennis ball. Why so? It's because of the factor of momentum. Yes, the rate of change of momentum is actually known as in the first law. Like F is equals to ma, the rate of change of momentum can be a derivative of Newton's second law of motion. Also, to understand the application of Newton's second law, there are many vivid examples. Like we can see players playing in the cricket ground. Why a fielder lowers down? Well, even in the training sessions, the bowlers and the fielders are all called upon by the trainers to actually lower down their hands when on the spur of catching the ball to reduce the momentum. Like if someone is throwing the ball and we are trying to catch it, we need to lower it down. When you do that, the momentum gets nullified or the effect of the speed of the ball gets reduced. Okay. And this is a hack which every bowler gets trained in their courtrooms by the trainers. The example could be a fielder lowers down his hands while catching a ball. Next, these are all certain examples which are getting asked in the CBSE boards. Newton's third law of motion, and which deals upon action and reaction. And for this, there are various kinds of numericals present. Also, one of the numericals which you have seen will be an application of it. We'll be considering it after considering the law. For every action, there lies an equal and opposite reaction. For this, one of the most easiest and relatable example could be when you blow up a balloon. Okay, you're taking a balloon, air balloon, and you're blowing it up, and you're calling it a release. When you're calling it a release, the balloon starts blowing up. Okay, the balloon flies basically. Why does that happen? Because when we were pressurizing the balloon, we were inducing our air into the balloon. And now, when we are calling the release of the balloon is releasing the air. So though the balloon is non-living, but yes, action-reaction pair, action-reaction effect basically does not hold any virtue with the substance to be living or non-living. But yes, it holds true and truth for all the cases. A balloon flies. When you call the release of it, on spur of filling it with air. Yeah. Now, one of the example questions which we can consider. In this question, the examiner wants us to find the minimum value of force to pick up the body. What could be the minimum value of force? We can see that there is no external agency. But what's keeping it in contact? That surface tension. Friction between the block and the table or the surface over which it is placed. Yeah. And yes, one more thing to notify. When we witness that there is no particular stipulation being given to us, that in terms of mu is not acting to be zero, that means there exists a mu. What is mu? Mu is the coefficient of static friction. Coefficient of friction, where you can see mu s is the coefficient of static friction, mu r is the coefficient of rolling friction, and mu s is the coefficient of sliding friction, respectively. Now, in this question, we can see that what we need to find the minimum value of force. Okay, so we should understand certain conditions. Like first of all, the components, the breakdown of components of the force. There can be the breakdown of components in two parts, f sine theta and cos theta, respectively, as we know, as we have done by far, and you will be covering it in all my upcoming sessions where we will be discussing the block body diagrams. Yeah. So the block is attached to the table, to the surface, and a pulling, a force is applied like this, diagonally. A force is applied. So we need to find the components of it. We are breaking down into two components, f sine theta and cos theta. The theta inclination is occurring from here. So on the vertex on which the theta is inclined is always taken as to be the cos theta. And the other end is always taken to be the sine theta. No choice. So cos should be taken into context, and then relatively you can find up the sine theta. Yeah. So when mg is greater than f sine theta, what is mg? Mg is the reaction force, is the normal reaction force. Yes, n is equals to mg. N is the normal reaction force, and it is equals to the mass of the body times the acceleration due to gravity. Okay. So if the mass is of 2 kg, 2 into the acceleration due to gravity, which could be 10 or 9.8, you'll be getting mg, which is equating to the n or the reaction force. Normal force is also known as the reaction force. Yes. So when it's less than f sine theta, then the case is not lifting. What is not lifting? The block is not lifting. The block is not leaving the surface. Okay. And normal is not equal to 0. But when you're getting it to be equal, f sine theta is equals to mg, just in a position of a lifted case, normal is equals to 0 and f is equal to, we are just substituting and transposing. Now from here, you have the grade 10 mathematics coming into play. F is equal to mg upon sine theta. Substituting the value of sine theta, you will be getting, which is half, you will be getting 2 mg. So the minimum force of the value should be twice of the mass and times the acceleration due to gravity should be the minimum value of force to pick up the body. Okay. I hope you all understood the topic, laws of motion. Keep practicing and I'll see you in the upcoming session. If you have any doubts or queries, please contact my Urban Pro profile. Thank you so much.